Hi, this video is about electric potential difference, how to calculate it, and how to use it to calculate some other things about electrical charges and electric fields. So, electric potential difference essentially comes down to being work that's done on a charged particle in an electric field. Most of us already know how to calculate work that's done on any regular object using the formula work equals force times distance. Essentially, the same formula can be used to calculate the work that's done on a charge moved in an electric field. We can use the force that it takes to move the charge through the field multiplied by the distance that it's moved through the field. Now, usually this is expressed as work done per unit charge, and this is called an electric potential difference. Electric potential difference is the work that's needed to move a positive test charge from one point to another divided by the magnitude of the test charge. So that you notice that potential energy, the potential energy of an electric field here, has nothing to do with the size of the charge that's in it. Okay. Now this is also called voltage, and it's measured in volts. 1 volt is equal to 1 joule per coulomb. Okay. Joule is the unit that we normally use to measure work. Coulombs are the units that we normally use to measure charge. Okay. And the formula for electric potential difference is W divided by Q. Okay. That's work divided by charge. So we get some different effects when we move different charges around in different fields. Okay. To get a positive electric potential difference, there are a couple of different things you can do. Okay. You have to do work against the electric field to get a positive electric potential difference when you move the particle from one place to the other. That means that you're fighting against the forces in the field. You're moving two particles closer together that don't want to be closer together, or two particles farther apart that actually want to be closer together. So a good example is moving a positive charge away from a negative charge because they're attracted together. You're working against the electric field. Or moving two positive or two negative charges closer together because you're having to put force in, apply force to get these things to move closer together. All right? A negative electric potential difference is the opposite. To get a negative electric potential difference, you're having to move things along with the electric field that they're in, the way they would naturally want to go. So you experience a negative electric potential difference when you move that charged particle along those field lines. For example, moving two positive particles farther apart, or two negative particles farther apart, or if you should move a negative and a positive charge even closer together. Those are the natural directions that those particles want to go. You're not actually having to put a force into that. You have to put a force in to stop it from happening. So that's why you get a negative electric potential difference there. You're not actually putting any work in to make this happen. You'd have to apply work to make it not happen. That's why the electric potential difference there is negative. Okay. It's also possible to get zero electric potential difference. And zero electric potential difference is kind of a special situation. Not entirely, but a little. Sometimes there's absolutely no difference in that energy between the two positions. One really good example is if you move a particle around a charge in a circle. So along this line right here, around the Q at the center. Each one of these places around the center is exactly the same distance from the center as the others. And therefore it has the exact same amount of energy. And no work's done to move them from one spot to another. So you get zero electric potential difference. Okay. So any charged particle that orbits another charged particle is experiencing zero electric potential difference as long as the orbit's in a perfect circle. Now, we talk about electric fields around point charges a lot. those electric fields aren't uniform. They're not even. They curve, they move out at angles, they get weaker as you move further away from the center. But we can create uniform electric fields that line up in perfect lines and have essentially the same strength throughout. Okay, the best way to do this is by placing two large flat plates with opposite charges near each other. So that's one large plate that's positively charged and one large plate that's negatively charged, parallel and very close to each other. Okay. In this case, the electric field lines between them are perpendicular to the plates in straight lines, and the strength of the electric field is even all along these lines. Okay. If you were to place a positive test charge in this field, the force on it would be a constant force. Because of this, you can use the regular work formula, work is force times distance, to calculate the work that's done on this charge if it were to be moved. We could also still use the formula E equals F over Q, that's the electric field strength, is equal to the force divided by the charge to calculate the electric field's intensity, so that we can figure out the electric field's intensity between the two plates at any point in time. Okay, so we can definitely calculate the voltage in this situation with this formula. Voltage is equal to the strength of the electric field times the distance between the plates. So the difference in voltage from one plate to the other is simply a measure of the strength of the field times the distance between the plates. Now, the electric field intensity is very high near the positively charged plate and low near the negatively charged plate. So we can use all these formulas that we've been through to calculate some things. We're going to run through a quick example problem. If you have two parallel charged plates, okay, and the field intensity between them is 5,600 newtons per coulomb, and those plates are 0.06 of a meter apart, what is the electric potential difference between them? Now, the formula you're going to want to use is this one, okay? V equals E times D, or V is the voltage, or the electric potential difference. E is the strength of the electric field, and D is the distance between the plates. Now, we know from the numbers given us in the problem that the strength of the electric field, okay, is 5,600 newtons per coulomb. We simply input that number where E was in the original formula. The distance between the plates is 0.06 of a meter. Place that in the D and plug that into a calculator, work the math out on your own. Comes out pretty easily to show that the voltage difference, or the electric potential difference between the two plates, is 336 newton meters per coulomb. Now, if you figure that out in the units we know, a newton meter is a joule. Okay? And a joule per coulomb, we've already said earlier, was a volt. So this is also equivalent to 336 volts. Another example problem. The electric field intensity between two charged parallel metal plates is 5,600 newtons per coulomb. So these are the same two plates from the previous problem, and the plates are still 0.06 of a meter apart. Okay, how much work is required to move a proton from the positive plate to the negative plate? So this is a little bit of a different question. All right, we already knew the voltage. Now we're trying to figure out the work. A couple of slides ago, we said that work is equal to the charge times the voltage. All right. If you didn't know, a single proton has a charge of 1.602 times 10 to the negative 19th coulombs. It's called the elementary charge. It's the charge of one proton. And we've already calculated the voltage to be 336 volts. Right? So that we can plug those numbers into this formula and calculate that the work done here is equal to 5.38 times 10 to the negative 17th power coulomb volts. Now, a coulomb volt, if you do the math, is just a joule, because a volt is equal to joules per coulomb. Multiply that by coulombs, the coulombs cancel out, and leave you with just joules, which is the unit that we traditionally use to measure work. All right. When you apply a potential difference of 150 volts between two parallel plates that are 0.10 meters apart, what is the strength of the electric field between them? All right, we know this formula. We've been using this. We just know some different numbers than we've known before. So we know that the electric potential difference is equal to the strength of the electric field times the distance between the plates. Okay, we know the distance between the plates, and we know the electric potential difference. Okay, electric potential difference was 150 volts, and the distance between the plates was 1/10 of a meter. The only thing we don't know in this equation is the strength of the electric field. That's pretty easy to solve for. You simply have to divide both sides, okay, by this 1/10 of a meter to make it move from one side to the other. And when we do that, we get that the electric field, between the two of them is equal to 1500 volts per meter. Okay? If you rearrange the units in all of this, that actually comes out to 1500 newtons per coulomb as well. All right, and our last example problem. Okay. A voltmeter, which is a tool we use to read the voltage in just about any electrical circuit or any situation like this, reads 350 volts across two plates that have an electric field strength of 4,500 newtons per coulomb. How far apart are the plates? All right, once again, we know this formula. It's the same formula we've been using all along, where the electric potential difference is equal to the electric field times the distance between the plates. All we have to do is plug in the information the problem gave us. We know that the voltage is equal to 350 volts. Okay, the electric field strength, or E, is equal to 4,500 newtons per coulomb. Once we plug that in, it leaves us with only one variable left to solve for, which is D. Okay, using algebra to rearrange the formula, we find that D is equal to 0.078 volt coulombs per newton, which sounds like a crazy unit, but when you plug in everything we know about those units, you get down to the fact that it's equal to simply 0.078 meters, or 7.8 centimeters. Alright guys, thank you for listening to the presentation. Let me know if you have any questions down in the comments below, and I'll be happy to try and answer them.